And now it's my great pleasure to introduce Martial Hebert. Martial is a University Professor of Robotics at Carnegie Mellon University. Right after a PhD in computer science at the University of Paris, he joined CMU, where he became professor. He has had several prestigious roles there, such as director of robotics, director of the Robotics Institute. He is now the dean of the School of Computer Science. During his early years at CMU, he was part of the Autonomous Land Vehicles program, a precursor of all the research happening today on self-driving cars. Recently, he's focused on self-supervised learning for videos in the context of robotics applications. And this is what he will talk about today. His talk is entitled General Models for Computer Visions, right? Martial, the floor is yours.
Thank you, Diane. And Martin, you were a real speaker. I just want to point that out, okay. All right, the work that I'm going to talk about this morning is work with Jipeng Bao at CMU, Yushan Wan at UIUC, and Pavlo Stokmakov at Toyota Research Institute. Some of you might remember Pavel. He was a student here with Cordelia Schmidt. So this is all staying in the family in Grenoble, okay? All right, so let me introduce a little bit what I want to talk about. You'll have to bear with me because the transitions here seem to be a little slow. And okay, this is going to be interesting. All right, so what I want to talk about today is some ideas on learning features for video understanding for robotics. The basic problem that we're trying to address is that we need to understand videos for robotics in a number of different contexts, driving, robotics, observing people, etc., etc. We want to do this both from a temporal perspective as well as a 3D understanding perspective. That's where I use this buzzword 4D, basically temporal and 3D. And of course, we'd like to do that in as general a way as possible that can be applied to a number of different downstream tasks. And we also would like to do this with minimal supervision and be able to learn those representations in a self-supervised manner. So that's basically what we're trying to do. We want to be able to learn feature representations that can be applied to a number of downstream tasks and be able to do this with as little supervision as possible. Okay, so let's look a little bit more. Let's look a little bit more at what we mean by understanding videos. We can look at kind of two different perspectives. The first one, and that would be the first row here, is to view the video as basically something that is temporally consistent and include 3D information. It's basically a 3D view of the world over time. The second way that we can think of the video is basically, and this is illustrated on the second row here, is basically being a set of objects in a scene. Okay, so we can think of those two different perspectives. It's very difficult to learn representations that take into account all those perspectives at once. So we're going to split the problem into two parts. In the first one, Draco is the name of the computer. Draco is a little tired, and there's a little delay when I move from one slide to the other, in case you wonder what's going on here. Okay, so in the first one, we're going to look at the question of temporal consistency across the video and separating the video into objects that are temporally consistent over time. And we're going to propose a way to do object-centric compositional learning with minimal supervision, actually entirely self-supervised, to learn those representations. The second way that we can look at the problem, yes, is to think of the problem as observing scenes that are in 3D and trying to extract information directly from the scenes. And there we'll propose an extension of the ideas around NERF to not only generate new scenes from new viewpoints, but also generate properties of the scene. For example, segmentation, surface normal, etc., etc. So those are the two paths that we're going to take to learn those representations. And the third piece here is that we'd like those representations to be generalizable to different domains, different data sets, etc. So we're going to look at ways to enhance the generalizability of those features using ideas that are shamelessly borrowed from recent diffusion models. Okay? So that's what we're trying to do. So let's look at the first part. What we're going to do here is to take work inspired from slot attention techniques that basically say I'm going to take my input videos and I'm going to try to learn a representation that can separate the video, the feature representation of the video into slots that roughly correspond to different locations of interest, I'm choosing my word carefully, in the video. And then hopefully we can use that general feature that does this slot separation, if you will, in downstream tasks. And we want to learn those slot features using the video reconstruction as the signal, right? So we basically get videos as input. We learn a feature representation separated in those slots, those attention slots, that can then be used to reconstruct the video. And that's our initial way of doing the loss. The key challenge here in doing this in practice, in realistic video, is that we have this object background ambiguity. And in fact, if you look at the original work that was done in those kind of slot attention idea, those were done on synthetic data sets, like this one here, where this background object separation is a very simple matter. Things work very well. Things work very poorly on realistic video. In fact, they basically don't work at all because of the fusion between what we call the objects and what we call the background. So what we so again, this is basically the problem. We have confusion between what we call the moving objects that are at that particular frame in motion in the video. The things that we call dynamic objects, in other words, things that can but not necessarily motion at any given frame in the video, right? And things that are separated physical 3D objects. So what we did is to, which is basically separating the rest of the scene, basically objects that can move. And our solution to do this is to use motion cues, basically take this representation, the slot attention representation, still use the reconstruction of the video as the key driving objective, but add to it some rough slots that we get from the slot attention module. And by doing this, we can clean up basically the result and get something that looks like this. Now this is entirely self-supervised. There is no annotation of supervision of that process. This can be used in downstream tasks like object detection, object tracking, etc. Right? So again, this model generalized to non-moving objects, what I called a dynamic object. It's entirely self-supervised. Okay. Now, there are still issues with this, and one issue in particular is the issue of long-term temporal consistency. What we would like is for things that are extracted to be consistent over time, over long periods of time in the video. And as you saw here on this quick example, those things are very hard to achieve in real videos. Again, that's where we need to be very careful on what type of data we do our experimentation. This long-term consistency works very, very well on synthetic data, on toy examples, and again, it tends to fail on real data. So what we did to address this is to say, well, maybe we need more structured space instead of the feature space that we were using before. So this is where we are at this point, right, we have the input video, input images. We use the reconstruction as the loss and learn those internal features using our slot attention idea. What we're going to add here is to take those features, internal features that we learn, and discretize them, basically quantize them. And by doing this, we're going to end up with a representation that is much more robust and will achieve the level of long-term tracking, long-term consistency that we want to achieve. We're going to call those discretized features tokens, right? And the basic idea is to combine our slot attention approach that we had to start with the idea of quantizing the features, this idea of tokens. And basically combining the two is going to give us the robustness and the consistency that we need. This is a little bit more detailed. I'm not going to get into too much detail, but those are described in the paper. But basically, what we're trying to do is to combine two things. This slot attention mechanism that I described earlier, and the idea of quantization, and to have one helping the other by doing the joint learning of the two. This is a visualization of the kind of thing that we get. I can do it here. Now we have a consistency across images and achieving what we set out originally. All right. Okay, so this was one, there is one slide here that doesn't show for some reason, but of course comparing to the competing so the second part now that I want to talk about is looking not at the objects and the temporal consistency, but looking at the scene and the 3D aspect. And let me start by reminding you of the basic approach for building implicit scene representation, things inspired from NERF and related technique, where we basically have a bunch of images. We build an implicit internal scene representation from which we can render new images and generate new images from new viewpoint. Okay, so that's the basic idea. The question now is, can we use the same ideas to, instead of just generating images, generating other descriptions of the scene. So for example, being able to generate surface normal, segmentation, shading, etc. Now, you could always generate the image and apply your favorite segmenter, for example, to the generated images. But what we will show is that you can do much, much better if you learn the internal representation in a way that will allow you to do those multitask output in the first place. So that's the basic idea here. So what we're going to look at is using a conditional NERF so that we can learn an internal representation from multiple scenes, use it on a new scene, and what we want to do again is, instead of just predicting the image, to predict other properties of the scene and to learn the internal representation so that we can predict those additional properties. So this is the initial setup. This is the first setup that I'm going to show is a little bit of a naive setup. We're going to assume a lot of things. We're going to assume that we have ground truth on the output that we want, for example, segmentation, and we want to generate it on the new views. And then I'll generalize that a little bit to a more practical approach. So what we want to do is to generate from multiple views the output on a new target view given a new camera pose. And what we want to do is to learn the model, learn an internal representation that's going to enable us to do this. By output, I mean any of those scene properties, semantic labels, surface normals, any other property of the scene that we want to generate. So the basic question is, can we do this in a way that takes into account those multiple output, generate those multiple, learn a representation that allows us to generate those multiple outputs directly. So this is just the outline of the approach, and again, I'm not going to get into a lot of details of how this the implementation details, but the basic idea is we're going to take those input, learn a first representation, this blue feature VC, then apply a first module that will ensure cross-view compatibility between those features, and generate K, if we have K output, generate K new feature representation for K different tasks, again, segmentation, surface normals, etc. And apply a second module that will ensure consistency between those different tasks. And finally, generate the representation for those K output tasks. Okay, so the basic, irrespective of the detail, the basic idea here is to learn an internal representation that will allow us to generate those multiple output, those multiple tasks, if you will, for an input scene. This is a visualization of the kind of output that we get. Now again, those outputs are generated directly from this internal representation, not from the generated RGB. So we learn the representation to generate this directly in a multitask way. Those are qualitative comparison. So on the left is our output. Maybe it's our output. On the right is the output that you would get if you did what I call the discriminative approach. What I mean by that is simply taking the generated RGB images, right, and generating the output using a standard approach, right? Now, the interesting an interesting property of this also is that we can generalize to out-of-distribution scenes. So this is an example. Here, those are outputs on two data sets, blended MVS and Tartan Air, for the model trained on an indoor data set. Okay, the GeoNerf is one of the related state-of-the-art, and MovieNerf is ours. The bottom line here is that that baseline does not generalize to the new scenes because they're too far from what it was trained on, whereas this model does generalize much more precisely. We can show that more quantitatively. The gray line here is ours, and this is compared on a number of different baselines with two related techniques, semantic nerf and SS nerf, who are two other techniques that try essentially to do the same kind of thing, meaning to be able to generate not just the RGB image, but generate other properties of the scene from the representation. This is better performance across the board on all of the metrics of the different properties that are generated. The other baseline that is important to compare to is what if we generate the image as is standard with those kind of representation, and then apply another process to generate the output, for example, semantic segmentation, right? That would be the most obvious baseline to do. And there again, now there's different variation on how to do that. You know, different ways of training those things, and across all of those, we get also better performance. And that's not surprising, by the way, because what those techniques would do is to ignore the consistency across the task and ignore the consistency across the view. So it's not surprising that we would get better result by doing all this consistent representation, if you will, and learning that consistency at learn time. Okay. Now, I cheated a little bit. Actually, I cheated a lot by making some assumption as to what was available in those views that we have to begin with. In reality, in a real application, this would not be available. So we can still deal with that. And the idea is, I'm not going to show a complicated diagram, but the general idea is this. Imagine, so you don't have any information on those views about those properties, segmentation, normals, etc. So what you can do is to generate those properties using some other network. Now, I just told you just one slide ago that that doesn't work, right? So where am I going with this? So what we can do, and this is where the diagram gets a little complicated, so I'll say it in words. What you can do is to start with a network for each of those properties, each of those tasks, and then retrain that network jointly with learning that internal representation, right? So in other words, you learn how to generate that data for the views that you have as input, and at the same time learn how to generate that internal representation. The bottom line is that you can still do that generation of properties, right, of scene properties, without the annotations in the first place, right, which is, of course, as a practical matter, what you need to do. You cannot assume that you have those. Is this a movie? Okay, so this is an example here, a simple example here, where this is an input image from one of those sets. The left column is what you would get from what I call the discriminative approach, meaning generating RGB and then processing it. The middle one is ours, and this is the ground truth on the right. Now, when I say by ours, it's again this process starting with an initial discriminative approach, if you will, and then jointly train that network, those networks that generate the output here, those surface normal in this case, and jointly train that with the moving nerve that I showed earlier. Okay? So the bottom line is that we can actually make it work without the annotation, right? I told you I cheated at the beginning, but we can make it work without this cheating and without those annotations, which are not available in reality in a natural system. Okay, so those were some ideas on first learning representation to do the object and temporal analysis of videos in a self-supervised fashion. And the second one was some ideas on how to learn representation to extract properties of a scene. The third thing that I want to talk about, which is much more prospective, the previous one are all published, by the way, in various places, CVPR, CCV, and all this. The third one is not, so this is more exploratory. And this is the idea of asking the question, how can we make those features more generalizable? Okay? In other words, that if now we use a different domain, a different type of data, can those features generalize to this new data? Those are some examples here. Obviously, if we try to use the kind of things that I showed on radically different domains, outdoor, indoor manipulation, etc., we're going to get poor generalization of those things. So what we would like to do is to do a large-scale model that can capture more information and be able to generalize better to new environments. So we take inspiration from, some of the standard work that is going on around. This is a picture from the standard paper on large-scale diffusion model, which basically says we can learn very powerful representation by basically adding noise and trying to reconstruct the original scene based on the prompt. Okay, that's the basic picture. This is not from us, of course. That's the basic picture from diffusion models paper, and one can show that using those kind of models you can generate a very general broad range of output. Okay, so this is in the context of generating images, right? And what one shows in those papers is you can generate things that are very far from the original data, in fact things that never existed, like the one on the right here. Okay, so that's, again, that's not us. This is standard stuff in diffusion model. So one idea is to say, well, why don't we do the same thing, right? But instead of generating RGB, let's generate what we're interested in, which is those scene properties that we're interested in, whether it's segmentation, surface normals, etc. And let's see if that, using features that are learned that way, can help in that process. This is an example here where by doing this, we can, again, this is a simple example on surface normal output, showing, again, the margin of what we, the increase in performance by doing this, and also being much more robust for changes in the type of data, the open vocabulary problem. So this was one idea. The other idea combined with what I presented at the beginning on the slot attention approach is to say, well, instead of using the usual prompt like this, perhaps we can use as input our slot representation that we learned before. And then we can basically do the same kind of idea as in the diffusion model, but with this slot attention representation as being the prompt instead of text. Okay. And maybe by doing this, we can learn a more generalizable representation, just like what happens in standard diffusion models. Okay, so those are some preliminary results. Those are very still very simple scene. The interesting thing here is that we get reasonable prediction. This is on this object discovery task, but again but this time without any motion self-supervision, okay, and with the ability of moving across different data set type. Again, I'm not claiming any quantitative results here, but this is just to show you the basic idea of what we're trying to do here. Okay, so this is basically what I wanted to talk about today, basically looking at different aspects of video analysis, trying to learn feature representation that address different aspects of this problem, and in particular being able to learn them in a way that is self-supervised, requires minimal supervision, and can be generalized. So we looked at compositional ideas based on slot attention ideas. We looked at extension of nerve type ideas to learn those representations, in particular representation that capture the 3D structure and are able to generate multiple types of output for multiple tasks. And finally, we talked a little bit about using the most recent idea, like diffusion models, to be able to improve the generalizability of those features across different environments. So that's basically what I wanted to talk to you about today, and that's the end of my talk. Any questions?
Okay, so I guess I can start with the first question. And like across these presentations, you've shown that you want to understand what's going on in the scene in the least supervised manner. And I was curious about like how much do you think of the geometry will emerge from this discovery, unsupervised understanding of the scenes, and how much do you think the geometry should still be hard-coded to perform some of the tasks? Do you have a take on that?
Yeah, that's a difficult question. The approach we took here is to go in one extreme direction, especially in the first part, right? Which should basically not have any geometry at all, right? Personally, I think, especially where I come from originally in terms of my work, I do think that we can go further by having more explicit geometric representation in the system. But I do think at the same time that there's a lot of value in trying to see how far we can go using this kind of approach. I don't know at this point what the right balance really is.
Okay, thank you. Is there any question in the room? Yeah? Yeah, good.
Well, excuse me for my short-term memory, but at the beginning there was this object that can move, segmentation. So how do you define objects that can move again? Because the building can move if there's an earthquake, but it was more like the cars.
Yeah, it's basically objects that have motion signal of some kind in some of the data.
So the parking car, is it because it's semantically a car, or
yeah.
okay?
Yes.
And it comes from the data distribution.
Yes. Yeah.
Okay.
So this was the importance of adding the motion guidance. And by the way, one thing that's a little bit misleading in what I showed here, you may not have noticed, but the picture I showed in the motion input looked like it was a pretty good motion. In reality, we need very little motion signal, right? So as long as there's some motion signal on those objects somewhere in the training set, okay, it will eventually converge. And that's very important because otherwise we're moving the problem, it's a moving target, right? We're changing the problem from that segmentation or slot attention problem to an even harder problem, which is to have the precise motion segmentation. So we do not require the more precise motion segmentation. All that we require is there's some motion signals on those objects.
Okay. Okay, got it. Thanks.
I have a question regarding the diffusion idea that you have. It sounds a bit counterintuitive that you say I have this nice input image where I do some separation or whatever task you want to do, but I have first to do like a noisy image of it to give it then to the diffusion model to then make use of the diffusion model. It sounds for me a bit counterintuitive. Instead of using maybe directly the nice input crystal, nice input image that we have. So I'm wondering if you think that this is just now kind of some side effect because you're using the diffusion model, or that we can overcome this and get rid of this noisy input that can introduce some randomness or problems maybe.
Well, the noisy part is precisely, I think, is precisely what's important by introducing that randomness, right? And forcing the system to reconstruct the image, right? That's kind of why there's this generalization that is achieved. Right?
Yes, it's not my domain, but I'm always curious about, do you think about a special processing of objects appearing in the scene? Because, you know, you have cars bumping into the scene or disappearing and so on. It looks like in most of the video I've seen on object detection or object tracking, there is always this problem of part of objects which are, you know, introduced new in the scene. So how do you think that you need a special processing of this events?
Yes. Thank you for asking the question. The new object appearing in the scene, that is not a problem. They're just going to be on another slot. That's fine. The problem is more objects that appear and reappear, right? And the issue of long-term consistency when there is large scale. The reason, so we are addressing this as part of this overall project. I didn't talk about that because that's not our work. This is work from University of Michigan, Andrew Orwens. Now, you need to do a little more for this. You need to have a little bit of more detailed tracking information or consistency information, right? But that's something that they look at, and they look at this, specifically this issue of the disappearing and reappearing, okay? Combined with what I showed at the beginning, okay? I did not present this because, like I said, it's not our work, but yes, that's being looked at as part of this project. I can point you to those papers offline.
Any more questions in the room? Maybe online? You know that for people attending online, you have the chat that allows to ask questions at the end. I know there's a little bit of delay, but hopefully I will manage to catch all the questions that have been asked. No? Then maybe I can wrap up with a more general question. Or is there anything you want to share where you see the fields of AI for robotics going? And what do you think will be the biggest challenges in the years to come? Is that something you would like to comment on?
You don't have a simpler question? Something easier, maybe?
Well, it's not fun if it's too easy, right?
I'll answer it that way. If we look at everything we do in AI and robotics, one of the key challenges that I think we have not yet addressed is this issue of correctly characterizing, evaluating, assessing, whatever word you want to use, the performance and implementation of it, right? And this is the central goal to the deployment in practical applications. At CMU, we do a lot of things in critical safety issues, driving various field robotics applications and that kind of thing. If you compare to classical engineering for those kind of systems, you have a bookshelf of worth of techniques, from formal mathematical techniques all the way to best practices in testing and evaluation and all that. And we pretty much don't have any of that in AI and robotics. Now, when I say that, people think that's just deep. Deploy. What I mean by that is that the progress and our ability.
Thank you very much for this very insightful answer and for a great talk. So yeah, thank you, Martial.